going to talk about stall speeds this afternoon. And like I said, it's a fairly short lecture, so hopefully we'll get out of here before the 2 o'clock whistle blows. But stall speeds is one of the more important things we do in plate test because almost everything else is tied to it. The FAA chose for fixed-wing airplanes to put even handling qualities as a function of some multiple of stall speed, like 1.4 times the stall speed, or 1.3 or 1.5. Those kinds of things end up being your trim speed, so you need to know what the stall speed is in a given configuration in order to do that. They also say that although they require you to do power on stalls are not very repeatable in many cases. Getting the numbers are not very repeatable, and so as a result, the stall speeds they talk about in the rules are power off stall speeds, or power for zero thrust. However, if you do zero thrust, you have to calculate what zero thrust is, so most folks just use idle power or power off and accept that stall speed. The FAA will accept either one. However, a lot of times companies will do this. Since the performance requirements are based upon stall speed, some multiple is a rule of stall speed. For instance, takeoff climb is 11.5 times the stall speed of the rate of climb it equals 11.5 times the stall speed in knots. Now you might say, where's 11.5 come from? Well, used to be 10 times the stall speed in miles per hour. Okay, and 1 knot is 1.151, okay, so that's where the 11.5 came from, okay. But anyway, the performance requirements, that used to set the gross weight of an airplane, the maximum gross weight, okay, that climb requirement, that takeoff climb requirement, because it's in the takeoff configuration, gear down, flaps in the takeoff configuration, that sort of thing. And an airplane had to climb 10 times stall speed miles an hour, or 11.5 times the stall speed knots. Okay, so that was the requirement, and that generally set the maximum gross weight or the useful load of the airplane. So, you know, the stall speed is quite important, but it's generally based on the power off stall speed. So here's what we're going to try to take a look at during this lecture. We'll talk about the data reduction of how we do that. I've already said most of this probably already. Need to determine it early in the flight test program since everything else is based upon it. It's usually the second thing you do after the airspeed calibration. So our second data flight in this course will be measuring the stall speed. Well, it's difficult to determine because of position error. It's hard to define at high angles of attack. We talked about that last hour. And in that region, the position correction changes quite rapidly. Usually as you approach the stall, position correction may be pretty good, and then it goes, you know, almost asymptotic, and you say, oh, you know, so where is it? So it's a good idea, you know, to spend a fair amount of time in the airspeed calibration at the low speed near stall. Well, the other problem we get into with stall speed is definition. Up to this time, you've probably assumed the aerodynamic definition, where the stall speed is equal to the square root of the load factor, N, times the weight of the aircraft, okay, over CL max times dynamic pressure, Q, times the wing area. things then, you know, these things all sound nice when I say them. In the real world, they're not so easy to determine. For instance, the wing area. What happens when you go through the fuselage? How do you consider that area? Do you just take it straight across? Do you, since it may cause a bump in the lift distribution, do you, cut it into the center line? A bunch of different things. All I can tell you is when you determine wing areas, when you settle on one, be consistent. Do them all the same way, okay? Do them all the same way. CL max, well, what is CL max? We say it's the maximum coefficient of lift, right? However, when you get to doing that in the real world, you find that curve gets sometimes pretty flat up there. And sometimes it'll even bump a little bit and maybe go up again, okay, depending on the airfoil, so it's different. Okay, the next definition, the military specification, calls it the highest of the speed of steady straight 1G flight at CL max. Now that sounds semi-straightforward. However, this causes a problem in making a comparison between FAA test done at the most forward center of gravity and military tests, which they try to get CL max, so they do stall speed at FCG. So the tail download is the least. I once did a exercise while I was as part of the military reserves on the KC-10, which is the military variant of the DC-10, okay? There was 10 knots difference between the FAA stall speed and the military stall speed because FAA stall speed was done at forward CG, military stall speed for that airplane was done at aft CG. 10 knots. And difference in the way it was done. And we'll talk more about that. So all of a sudden, this gets complicated because of how we define it. Oh, I mean, the first part of this looks pretty good, but you look at the last part, the speed at which abrupt loss of control occurs about any axis. Or the speed at which intolerable buffer or structural vibration is encountered. I was told by a friend of mine that at Boeing, when they did stall speeds, they actually put an accelerometer under the pilot's seat because the buffet was so great. And this fellow who worked for the FAA told me that he says the Boeing flight test engineers on the back trying to get the lowest stall speed they can get are going go, 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 And the pilots have lost, their headset is off someplace in the back of the airplane. They think they're going to have their teeth chipped. The vibration and buffet is so bad while they're doing this, trying to hold this thing in to get the very lowest stall speed. So, intolerable buffet. Military says you stop when you get that. FAA says, no, that don't count. Here's the FAR Part 23 definition that we'll use for the Cherokee 6. An uncontrollable downward pitching motion of the airplane or until the control reaches the up stop. Now, I can tell you this, I have yet to fly a general aviation airplane, and I've flown over 250 different models. I have yet to fly a general aviation airplane that the uncontrollable downward pitching motion occurred prior to reaching the upstop. So essentially, it's defined by the upstop. And the rule now says that in addition to that, you have to hold it on the upstop for 2 seconds to make sure you've really got a stall. Well, that's a Part 23 definition, but look at Part 25. The FAA can't even make up their mind what their definition is. VS is the calibrated stalling speed, or the minimum steady speed in knots at which the airplane is controlled. Now that's different than the one up on top. That's the big airplane rule on the bottom, that's the small airplane rule on top. So you can see how this gets kind of muddy due to the definitions. VSO. VS1 is the stalling speed in any specified configuration. VSO is the stalling speed with gear and in the landing configuration with gear and flaps full down. Okay, that's the difference in those definitions. So if you see VS1, it may be flaps up, gear up, okay? But it also may be flaps 10, gear up, gear down. You have to define, if you use VS1, it has to be defined, the configuration. VSO, if you see that, you know it's in the landing configuration. Gear down, flaps down. Okay, here's the configuration for determining VSO. Again, the engine's idling or zero thrust, and like I said, you know, zero thrust will give you generally a little lower speed than engine's idling, because of engine idling on a propeller-driven airplane, you're taking energy out of the air. And so you may not have the amount of up elevator that you do at zero thrust. So you may not get as low a speed at engine's idling. Propeller in the takeoff position, landing gear down, flaps in the landing position, cow flaps if the airplane has cow flaps closed, center of gravity, most unfavorable in the landing range. Again, that's generally forward CG at maximum gross weight. Maximum weight, maximum gross for the test in question. Now, the rule also says that for a small airplane, the maximum weight should, or the VSO at the maximum weight shouldn't exceed 61 knots. Used to be 70 miles an hour, okay? When the Cherokee 6 was certified, it was 70 miles per hour. Today, under 23, it's 61 knots. The reason for that is they found that survivability of accidents is a function of the approach speed squared. So they tried to keep it very low so more people survived. Okay, that's for single-engine airplanes, is the 61 knots. Or multi-engine airplanes of 6,000 pounds or less, i.e. Piper Seminole, that cannot meet single-engine climb requirements. Many airplanes, multi-engine airplanes, will not climb on one engine. In fact, there was an airplane lost here at FIT several years ago, where they took off from West Palm Beach after having come from the Bahamas. I think they cleared customs at West Palm, took off, lost an engine on takeoff, and crashed, attempting to go around. Was run way ahead of them. Pull the other power back and land when that occurs. Okay. But they've been used to flying the airplane with 2 people on board, and it'll climb in those conditions. 4 people on board. Light winds are, can be very dangerous. VS1, that's VSO we just talked about. VS1, calibrate stalling speed or minimum steady speed at which the airplane is controllable. Sometimes these things read a lot alike, but not necessarily interpreted alike. Well, the configuration, engines idling or 0 thrust again, propellers in the takeoff position, landing gear, flap, CG, and weight in the condition where you're going to determine the stall speed. They have to be determined, it's required that they be determined in flight using the procedures specified in FAR 2302 or 201, which is again those pitching uncontrollably or the control against the stop. Okay. FAR 25, again, goes through that. Minimum steady speed. In the transport world, what they will allow is that when the airplane stalls, the airspeed indicator will be unwinding. Small airplane world, we read the speed right when the nose pitches, or when we hit the stop, which is usually the same thing, okay? In the transport world, what will happen is the airplane has so much inertia. Big airplanes are heavy and they have a lot of inertia. Things don't change real fast. The airspeed indicator will continue to unwind, and the FAA has determined that you can, they define the stall speed in those airplanes as when it stops and starts back up. And again, the same kinds of things. Again, the most unfavorable CG, and here's where the difference became on the KC-10 between the FARs and the mil-spec. Here's another thing I haven't understood between big airplanes and small airplanes. The trim speed for small airplanes is 1.5 times the stalling speed. Now you may ask, how do you determine what 1.5 is when you haven't stalled the airplane? Well, you calculate it the first time, okay? And then after you stall the airplane and get an idea where it was, you go back and retrim for the new 1.5 before you do the next stall, okay? But for big airplanes, they allow you to give you a trim range between 1.2 and 1.4. I don't understand why the rules allow that, but that's what they say. Deceleration rate, 1 knot per second. 1 knot per second works out is pretty close to 1 G. Isn't exact, but it's pretty close to 1 G if you really maintain that until you get to stall. And of course, then they require you to meet flight characteristics that says you can't roll off more than 15 degrees and roll or yaw. Here compares the two rules. 23201 is wings level stall. You don't have that in 25, you have 23203. Generally, you can just compare these last numbers across rules. Here it's for turning flight and accelerated stalls. They don't have those for transport airplanes, but they do have critical engine and operative. See, these two rules compare 23205, 25205. And then there's requirements for stall warning, both of them. So generally, you can go jump back and forth using these last three numbers in the FAA rules. Well, other requirements, the regs discuss three-axis control prior to the stall and after the stall. Prior to the stall, you should not have, you should be able to maintain the wing level without yaw. After the stall, you should have not more than 15 degrees of bank or 15 degrees of yaw. During turn and accelerated stalls, you're allowed more. Critical engine inoperative, you're allowed quite a few. And then any warning prior to the stall, there's a specified range that the stall warning horn has to come on within. And that's usually, well, it's usually above 5 knots, but generally not too much above 5 knots, okay. Stall definitions: uncontrollable downward pitching motion of those or elevator reaching the stop. Again, we'll try to load this for most forward CG, so when we do this for real, we're gonna have to, we have some ballast we can put in the nose baggage compartment to help you move your CG forward, but we're probably gonna have to arrange our seating a little bit so we get the most forward CG with each flight crew. They require that you set the elevator to the minimum of deflection. For instance, if, say, your elevator deflection is 20 degrees plus or minus 2 degrees. So you would set it at 18 degrees, okay? The minimum allowable deflection is where you set this for measuring the stall speed. Prior to the start of the testing, set the flaps to the most unfavorable side of the deflection tolerance. Again, the same kind of thing. If you had 40 degrees of flap deflection, plus or minus 2 degrees, you'd set it at 38. That would give you the highest number. And during the test, you're going to perform several stalls in the same condition. Generally, I like to do about 5 if I can, so I've got a reasonable statistical sample, because you won't get the same answer on each one. You'll vary a knot or two, okay? So we'll do half a dozen or so, and we'll make the corrections to the weight and that sort of thing, and then we'll average those answers to come up with the speed. Test technique: set the power to idle R0 thrust, trim the airplane to 1.5 or 1.2 to 1.4 for a big airplane. Establish a deceleration rate of 1 knot per second. When the horn goes off, you write that speed down. When the nose pitches uncontrollably or you've reached the up stop, you record that speed, record your fuel quantity or the time of day, depending on how you're determining weight, and then you have the data. What you require: trim airspeed, you'll write that down, whatever the 1.5 speed is. Fuel quantity, at least at the start of this thing, deceleration rate, and when you pick that up, the speed that you achieve, 1 knot per second. Observe warning speed, observe stalling speed, observe pressure altitude. That's not real critical, but worth recording. Ambient temperature, what the configuration was, what your power setting was, and any other pertinent comments. Now, well, correcting the data, we're going to correct the stalling speed for instrument and position error, okay? So we go into our lab book and we determine what the instrument error is at that speed. We make that correction, Then with our airspeed cal that we got the first time we flew, we're going to apply that to that instrument corrected speed. And then that's going to be this test speed, okay? To get the actual speed, we're going to make a weight correction because our weight won't be at the standard or maximum gross weight. So the standard weight, or maximum gross weight, is right here. This is the weight we were actually at when we got this number. So we'll have to do a calculation based on how much fuel we burned when we did that particular test to determine our weight. We'll know what our takeoff weight was, right? We'll calculate that here in class. We get to the airplane, we'll determine what the fuel state is. And if you flew first, well, we're gonna use the starting weight, okay, of 50 gallons of fuel. And well, let's say we've flown for 20 minutes before we get that, and we burned, so many pounds per minute. Multiply that by 20, and we get a weight, and we subtract that from our takeoff weight, and we get the test weight, which is this.